Um, I solve a problem every day to keep my mind relevant. This is 3405. Count the number of arrays with k matching adjacent elements. All right, watch this. Ooh. All right. Can't start without these babies on. Oh, all right. So this is a very frustrating problem. Why? Because it's a programming problem, but when you actually go through the description, you'll pretty quickly discover that this is a counting problem, right? This is a combinatrix. What do they call it? What's the phrasing here? This is a combinations problem. This is one of those problems that you probably saw in your discrete math class if you went to university, an advanced statistics class, right? One of those. How many ways can you distribute these elements in these bins given these constraints? This is just one of those problems, and I don't really know if this suggests anything in terms of your capacity to program. It definitely is an indicator of how well you understand, mathematical concepts, and it requires a high enough IQ. I'm not saying you have to be a genius, but you have to have a high enough IQ to be able to understand, some combinations, permutations type of concepts and apply them to problems. But I feel like this is a very unfair problem to be given in an interview because it's not a programming problem, right? This is a math problem. So this is one of those programming problems where it seems like a programming problem because it's on a programming platform, but the reality is that it's just a math problem. Okay. So with that said, let's go ahead and get right into this math problem and let's do some some combinations, permutations, and figure out how we can use that to solve this efficiently, I suppose. Okay, so within this problem, you're given three integers, n, m, and k. Okay, so just to use this expensive tablet, that's not that expensive, we have n, we have m, and we have k. Okay, so what do those things do, my guy? A good array is defined as the following. It's of size n. Okay, so this is the size of the array. I guess that's good to note. All right. Each element in the array is in the inclusive range from 1 to m. Okay, so we have this array of size n. So, there's all of these. So there's n elements. Now, if you've taken discrete math or some advanced statistics class, right, it's a common way that we formulate what we're writing just to try to get us a general idea of like what's the structure of this array, what does it look like in a very general sense. Okay, and then it said from size 1 to m. So each element in this range can be m things. Okay, right? Because it can be each element here can be 1, it could be 2, it could be 3, it could be all the way up to m. Just wasting time, just putting things on the paper. Sometimes just putting things on the paper is all you need to get you to some place where your mind can understand what the heck is going on in the problem, okay? Exactly k indices I, where I is greater than or equal to 1, less than or equal to n, satisfy the condition where array of I minus 1 equals array of I. Okay, so that means that there's k places, right? There's k places, so that's where these elements are the same, right? So there's k instances where that happens, right? Maybe another one's here, for example. I don't know exactly where, but right. The idea is that k of these elements are the same. So that happens k times, right? So the adjacent elements, right? That's array of I minus 1 equals array of I, right? So the element at the previous index equals the element at the current index. I guess this has some programming in it because you need to understand how to read this, and to understand how to read this, you probably need to understand something about programming. But we can already kind of tell that this is a combinatorics problem. Right? When I started reading this, I pretty quickly figured out, oh, this is a problem using combinations or something like that, right? And sometimes you don't know if there's like a closed form solution, I mean like there's like a really quick way, right? There's in one statement, can I use this information and plug it into a formula and get the answer? Or is it something where like there's some combinations to it, but I still have to do calculations to get the answer? And that's determined just based on, starting to, kind of walk through the problem, massage it, look at some examples, and from that you can determine whether or not, or what the answer looks like. Okay, we're going to return the number of good arrays that can be formed. Right, so good arrays are the things that meet these two constraints, right? So all the elements are between 1 and m. There's n of them because it's the size of the array. And there's k cases, right? There's k places where the previous element equals the current element, right? It could be any k places, but it has to happen exactly k times, not more than k times, not less than k times. Okay. Now, since the answer may be very large, return it modulo 10 to the 9 plus 7. That's just standard. Keep it within some range, so for time complexity. Okay, so this first example, I'm going to do the second one because it's a little bit more complicated. Okay, so notice that we don't really know, we know the structure of the array, but we're not like given an array or something. So using this kind of general form is probably the most preferable. Right, but if we go to an example here, right, where we have n equals 4, we have m equals 2, and k equals 2. Okay. Now, it says the answer is 6 and that these are the good examples, or the good arrays. Okay, so since n equals 4, we know that there's 4 elements. So 1, 2, 3, 4. Let's just walk through some random examples and see if they're good and why they're not good, or they could be good. Well, one thing we know for it have to be, one thing that has to be true in order for it to be good is that all of the elements are between 1 and m. So all the elements are either 1 or 2, right? Because it's between 1 and m. So let's just do one example here. 1, 2, 1, 2. Is this one of the good ones? No, it's not one of the good ones because there has to be exactly k equals 2 places where the elements are the same, right? The adjacent elements are the same. So that's not good. Let's do another one where I know it's going to be good. 1, 1, and 2, 2. This one is good. Why is it good? Well, let's ensure that's in that list. 1, 1, 2, 2. Well, it's good because, well, we have k equals 1 example where 2 adjacent elements are the same. K equals 2 where 2 adjacent elements are the same. The length is 4, and everything's between 1 and 2, so it's between them, so this is good. Right, and then we can go through the rest of these examples, right? 1, 1, 1, 2 is good because, the adjacent elements have to be the same. 2 adjacents are the same, 1 and 1. Another adjacent are the same, 1 and 1, so that's k equals 2. Everything's between 1 and 2, right? These 2 adjacent are the same. These 2 adjacent are the same, right? So they don't have to be distinct from each other, right? Like in this example, they're distinct from each other. But for another example right here, right, when we have, when we got 1, 1, 1, 2, it's a little bit harder to see, right? But this is your k equals 1 example, and this is your k equals 2 example, right? So there's some overlapping there, and that might make you a little bit more. That's kind of what had me stuck for a little bit because I was overthinking the problem. Right? This is with combinations is usually the issues that you're overthinking, right? But as long as you structure what you're doing correctly, you should be able to get to the answer. Okay. So how do we get to the answer from here? I think we should understand now, right? What does it mean for it to be good? Well, it's of size n. All the elements are between 1 and m, and there's exactly k cases where adjacent elements are equal. Okay. So the best way to solve these is to start from a very general case, okay? So let's go back to this example where we have n, m, and k, right? So remember we have n, m, and k. All right. So we're going to have n elements. Okay. Now, how do we want to go about this? All right. First thing we got to do is, one thing to do is turn your glasses upside down, right? Because you got to be able to see the world in a different way. That's the lamest joke ever. It's funny. I sometimes look at the metrics, like the YouTube analytics for the videos, and like every time I do something really silly, I lose like all the views. I go from 100 views to 50 views. So I go from nothing to basically nothing. Wait, I don't know. Okay, so how can you play around with this to try to get a formula? Well, the simplest thing here would be if there was no k constraint, right? If there was no k constraint, that's kind of like how I like to solve these problems. Is like start from something simpler and try to add in constraints and see what that does to your problem, okay? Because that would be the simplest thing, right? If there was no k constraint here, meaning there was no thing where like 2 adjacent have to be equal in k cases, and it was just how many good arrays would we have that just had to be of length n, and there were m things. There was length n, and each element had to be between 1 and m, right? So in that case, well, we could put m things here, and m things here, and m things here, and m things here, and m things here. So what I'm saying here is I have m options, right? Because I can do, in any of these cases, I can do 1, 2, 3, all the way to m. And what's the length of this? The length of this is n. So what is the calculation to do that? Well, I can put any m things here. I can put any m things here, right? Right, so if I put a 1 here, how many things can I put in the next spot? Well, I can put any of these m things, right? And if I put a 1 here, I could put any m things in these next spots. So I'm not going to do the calculation, like, I'm not going to draw it all out for you, but the idea is that if you have m options, you multiply them together. It's the product of them. And how many m's are there? So I'd have m options here times m options here times m option here. And how many times is this going to happen? Well, it's going to happen n times, right? And that's the same thing as m times m times m times m, n times. That's equivalent to m to the n. Okay, so if we didn't have that last constraint, it's a pretty straightforward calculation, right? If you've taken some sort of discrete math, statistics class, right? This is like one of the first things they teach you, right? Like, okay, you have a number of things, be any of those things, how many options do you have? You have m to the n. Okay. Now, let's look at the case where, to make it simpler, right, is let's introduce this idea of k. Okay, so we're going to make it a little bit more difficult. But let's say that k equals 0. What would that mean? Okay, so that means that there's 0 cases where adjacent elements are equal. So if k equals 0, that's equivalent to saying no adjacent equals. Nothing adjacent is equal. Okay, because k equals 0. How many adjacent elements are equal? That's k. And what is k 0? So 0 adjacent elements are equal. So what would that look like? Well, let's draw this out again. So we have n elements, 2, 3. Why am I counting? Well, it's the general n. Who knows? I'm a very strange person. Okay. And let's say k equals 0. All right. So how do we get started? Well, I can have still m elements here. Does that make sense? Where things get a little bit more complicated now is that in the next case, if adjacent elements have to be 0, what does that mean? Well, whatever element I put here in this first place, the next one can't be that. Because if I put a 1 in the first spot, I can put anything but 1 in the first slot. Because if I put 1 in the next slot. Because if I put 1 in the next slot, oh, well, look at this. They're equal to each other. That would mean that k equals 1 because there's 2 adjacent elements that are equal. So in order for there to be 0 elements that are equal, 0 adjacent elements that are equal, what does that mean? That means that this has to be m. I have m options, but I can't use whatever I used here. I'm saying in a general case, right? Whatever I put here, the next thing can't be that. So what can I put there? I can put anything but that. So, for a simple example, right, if we had, say we had n equals 4 and m equals 3, okay? So if I was to put in k equals 0, okay? If I was to put 1 in this first slot, I'm just drawing up one example of something that's valid. Well, I can't put 1 here because then that would be that those things are equal and I have k equals 0. K equals 0 means that there's no adjacent elements that are equal. So what options do I have? I can't put 1 there, right? My total options are 1, 2, or 3 because m equals 3. So I can't do 1. So I can put either 2 or 3, right? So that's the idea here, right? I can put anything from 1 to m here, but I can't use one of them again because that would mean that the adjacent elements are equal. So I have m minus 1 options here, right? And that's the same thing that happened here, right? I had 3 options, m equals 3, but I can't use whatever one I decided to use before again, or I'd have adjacent equals. So I have m, 3, minus 1 options left, that's just 2. okay? Now, what about for this subsequent element? Well, again, I have the options of 1, 2, and 3. Now I can't use 2. I can't use 2. Why can't I use 2? Because I used in the previous element, if k equals 0, nothing adjacent can be equal. So I have either 1 or 3 that I can put here, right? I'll just put 1 just for the sake. But that's the idea of, again, I have how many options? I have m minus 1 options because I can't use whatever's before me. This is a special case because there's nothing before it. Since there's nothing before it, you can put whatever you want there. But for every single one after, it's constrained by the fact that it can't be the thing that was before it. Okay, so that's true for all of these elements. Okay, so the formula now is, well, in this case, we still have m times, now how many elements is this? Well, it's the n elements minus the one element that I used here, right? Because this whole thing is n, but one of them is m, so the rest are m minus 1, so that's m minus 1 to the n minus 1 power, right? Because in the first thing, I can use whatever I want, but then after that, I have to always account for the thing before it since k equals 0 and subtract that out, okay? So just summarizing so far how we got here, right? We have this really simple case where there's no k constraint. It's just whatever you want to put there, you can put there. How many things can you put there? What does that end up getting you? M to the n. Now we have this special case of k equals 0, right? In this k equals 0 case, we introduce this m minus 1 idea because we can't have adjacent things being equal to each other. But we still have to figure out what are we going to do for the k not equal 0 case, okay? Think about that for a second. I'm going to think about how the heck we're going to do this, all right? Because there's a couple ways of explaining this, and I'm trying to remember because I did this earlier. I don't even remember how I managed to put this one together from here. Because that's always the problem when you try to build intuition. At some point, it always feels like the professor or whoever, the teacher, tutor, right? It's like they make a big step, right? It's like okay, 1 plus 1 is 2. 2 plus 2 is 4, and the integral of this is 4.x, lambda function. You're like, what? How did we just? But so how do we take baby steps to get to the final intuition? It's always a difficult thing. It's a difficult task. But let's see if there's any value to doing k equals 0 here. Notice that we haven't done any programming yet. We're not doing any programming. We're just trying to do math to figure out how we get to the final answer here. Okay, let's do it again. Let's do it with k equals 1 and see if from there we can figure out kind of the final idea here. So, let's do n, m, and then k equals 1. And let's, we'll write it out with, 4 and 3. Maybe we'll use that together, but so we still have this first thing where the first one can be m things. That's true no matter what, right? But what does that do for the rest of the problem here? Well, there's some place, right, where somewhere in here, either here, right, either in this slot, or in this slot, or in this slot, or in this slot, right, the elements are equal. Okay? So for example, if the elements were equal here, let's just say generally that the elements were equal here. Okay? These two elements, well, how many options, we're talking about options here, can there be? Well, this could it be any m things? Let's first start it here. Okay, let's start it here. This one on the left, I'm going to put a 1 here, and that might be a little bit confusing, right? This has to be, there's only one option for what this can be. Because it has to be, it's constrained by whatever is over here, right? Because they have to be equal, right? So if I choose something here as x, this has to be X. So it doesn't, it's always hard with probability because it's like, are you putting the element that's there? Or are you putting, I'm saying that there can only, like if whatever I put here, this is tied to it, right? So it doesn't add in, there's no additional options, right? It's constrained by this, right? Really, when you think about it, these become one element, right? So if the one thing doesn't make sense there, what I'm saying is that since these have to be the same, there's only one option for what can be there. Does that make sense, right? There's only one option for what can be there because they have to be the same. The adjacent elements have to be the same, okay? And you might say, well, I have m options. I could put any m options here. I could put 1, 1 here. I could put 2, 2 here. I could put 3, 3 here. Kinda, but you're victim to the same junk as before. And what do I mean by that? You're victim to the same fact that it can't be whatever was chosen here. Okay, so, if this was a 3, if this was selected as a 3, well, then you can't make these double 3. This was selected as a 2, you can't choose double 2. So you still only have m minus 1 options in this join cell. Now, for the sake of trying to determine what the probability is, I'm not going to leave it as 1. I'm just going to say that, you have m minus 1 options here, and this has to be a 1, and this is m. Now, this next thing can't be the previous thing, so now you're in the same case here, m minus 1, m minus 1. Okay? Right? Okay? All right. But what? So does this part make sense? I'm saying, if I wanted this to be the case for k equals 1, okay? What I'm basically saying is, I could still put anything in the first slot. If these two have to be equal, then that means that, I have m minus 1 options because it can't be this. Now, why? Because you can't make them equal, right? Like, we're just we're victim to the same idea, right? M minus 1 can't, like, we can't put the same thing here, or then these two would be equal, right? If these two were equal, now it mean that we had k equals 2, but we said k equals 1. If k equals 1, then there's only one adjacent pair that are equal. So that I can't have it be the same as this first one, or there would be two adjacent pairs that are equal. So there's only m minus 1 things that I could put there. Now I'm just restating it this way, just so I can keep the slots correct. And you'll notice what this is as well. I could put this 1 here, right? Meaning that, these things have to be the same, right? These two elements have to be the same. And, then the rest are victim to the same idea of m minus 1. Now, what makes this a little more complicated is that the position of this thing can be different, right? So if we copy this, right, because those don't have to be the adjacent elements that are equal. It could also be that these two adjacent elements are equal, right? And in that case, well, this has to be m minus 1 because, again, it can't be the previous thing because we're saying that these are the two that are adjacent that are equal. This has to be whatever is to its right, so there's only one option. It has to be whatever's here. This element is then m minus 1 things because it can't be the thing to the left, or then these two would be equal, and that would mean that k equals 2, but it's not, k equals 1 in this example. And again, this thing can't be equal to here, then these two would be equal, so that's also m minus 1. Okay. And then again, okay. What if we, now where's the last location? Well, I guess there's 2 more locations. Right, this has to be m minus 1. This is 1. M minus 1 that thinks that this can be. Then the last case here. This, I guess, would be a special case because it's always problems with directionality and probability, but if that doesn't make sense, don't worry about it. Right, this could be any m things. This would be m minus 1, m minus 1, m minus 1 after it. right? Because I haven't established anything yet. So this one's free to be whatever it wants. It's the one that the subsequent ones are always constrained, right? The first element's never constrained. And this is kind of like the first merged element. Okay? So one problem here now is like we have this rolling idea, and it's going to get even more complicated when let's look at k equals 2, and then we'll use this information. I'm kind of just going to brush through this quickly so that we can try to make a bigger picture here. So let's say n is whatever, m is whatever, and k equals 2. All right? So we have k equals 2. That means now we have two cases. I'm going to do two distinct ones. Right? There's two distinct places where they're equal. So again, remember the first one is m. Apologize. First one is m. Remember, these can only be one thing. This can be m minus 1 things. This can be m minus 1 things, and this can be m minus 1 things. It's just apply the same logic, right? There's only m minus 1 options here because it can't be whatever one this is. This has to be the same as that. So there's only one. It is a probability, like this has to be whatever this is, so it doesn't add any additional like combinations. M minus 1 here, and then another k here. Okay? So what you'll notice is that proportional to the number of k's, right, is the number of times you're going to see these ones. Right? Because when k was 0, right, when k was 0, there was no ones. When k was 1, there was 1, 1, right, in a single example. And when k equals 2, there's 2 ones, right? Because depending on the number of k, that's the number of items that are constrained, right? When there's k equals 3, that means there's 3 items that have to be equal to their... Oh my gosh, why am I writing all this? They have to be equal to their right adjacent. All I'm saying is if k equals 3, you know for a fact that there's 3 places, right, where these two have, like, things have to be equal to each other. So that means that there's 1, 2, 3 places where there's no additional probability in the problem, right? And if you want to just look at it like this, you say when k equals 0, there's 0 ones. When k equals 1, there's 1 1. And when k equals 2, there's 2 ones. And when k equals 3, there's 3 ones. So what does that do to our formula from before, right? This was our formula when k was 0. But now, every single time there's a k, we lose a 1. Okay, so let's go to... All right, let's look at this again. So this will be m. You know, a couple m minus 1s here. I'm trying to mix it up so you can see what's going on here. Okay. So in total here, right, there's still this m factor here, multiplied by what? Multiplied by m minus 1. But how many m minus 1s are there? Well, there's n minus 1 elements total. But how many of those have now been replaced by these 1s because they correspond to those adjacent elements that have to be equal? Well, there's k examples of that, right? So there's n minus 1 total m minus 1s. N minus 1 n minus 1 total m minus 1s. But there's k places where it's just a 1. So you need to subtract out those k places. Okay? But then the final thing is how do we take care of this weird example where it's like, where's the k going to be? How many ways can we move these k's around? Right? Because right now, this only accounts for one example. For example, here, right? We have multiple examples where, you know, maybe the k's over here, or maybe the k's over here, or the k's over here, or the k's over here. So then it becomes a part of how many ways can I choose the k's from the places that I can put them, right? Because I can put, for n equals 1, the k can be here. It can be 1 way, 2 way, 3, or 4 separate locations, So there's n minus 1 ways that I can do this. All right, now this is choosing. I hope you're familiar with this. N minus 1 places where I can choose to put those k1s. Right, so that's basically saying of all this area here, actually no, it would be of all this area here, what are all the locations that I can put these k's? N minus 1, choose k places to put those ones. Right, because, this is just one example. I could also have an example where, why did I do that? I also have the example where, n minus 1 here, and I put the k over here. And then there's another example where I put the k over here. Right? So there's I have k ways of choosing where I put it out of these n minus 1 slots. And why is it n minus 1? Well, because there's only n minus 1 adjacent slots, right? There's 5 slots here, but when we talk about adjacency, there's this adjacency, 1 adjacency, 2 adjacency, 3 adjacency, 4 adjacency. So that's n equals 5 minus 1 adjacent spots. So there's only 4 spots where I can put this one, right? The 1 can never be here because there's no element, right? The 1 can never be the most right element because there's nothing to the right to compare it to, right? So this is then our final formula. Okay, so to kind of recap here, we started with this general case of just saying, what if there's no k constraint? Well, then I have n elements, and I can make them any of the m things. So I have m to the n total possible ways of doing this. What if I have k equals 0? On k equals 0, I have no adjacencies that are equal. So I have m. I can put anything here, but in the next slot, I can't put whatever was put here. So I have m minus 1 things that I can put there. In the next slot, well, I can't put whatever I put here. So I have m minus 1 things I can do, so on and so forth. So that means the first one can be m, but the remainder have to be m minus 1. So there's m minus 1 things that I can put in n minus 1 places times that m for that final spot. Now when I have k equals 1, well, I still have this m minus 1 constraint, but for wherever I ended up putting that pair, that slot, right, that element is constrained to whatever's to its right. So there's only one thing that can be put there. So now, instead of having m minus 1 to n minus 1, I have m minus 1 to the n minus 1 minus k, because I have to subtract out the k places where it's constrained by the element to its right. And then finally, well, how many different ways can I put these k's? Because I can put these k's all over the place. Well, there's n minus 1 choose k ways of doing that. Okay, so where's the programming in this? Because all I'm literally going to do is get a page that won't load. What the heck is going on? You gotta be kidding me. This is so unprofessional. I tremendously dislike the updated Leetcode user interface. I don't know why they're enforcing this so much. Maybe I'll get accustomed to it and then prefer it. Right? That's one of the most unfortunate things about technology, right? Is that people tend to prefer the older GUI, even if the newer one is objective. I mean, how can you say it's objectively better? But even if the new one is better, but there's a certain overhead associating with getting the user accustomed to the new GUI. So even if the new one is better, they'll prefer the old one. So a common approach, and you've probably seen a lot, is that at a certain point they just won't allow you to use the old version. They'll force you to use the new UI until you're used to it, and then eventually you'll probably end up preferring that one to the old one. Okay. So where am I at here? Okay, so literally we're just going to copy this formula verbatim. So our answer is return. With such little programming, let's at least keep our indentation, right? We have m times, right, m to minus 1 to the power of, how many times can that happen? Well, we have n minus 1 minus those k elements that'll end up being 1. And how many ways can we do that? Well, that's dependent on the constriction, the allocation, I don't know, the way that we distribute those k's. And how many ways can we distribute those k's? Well, it's a combination of, there's n minus 1 ways to do it. There's n minus 1 adjacencies where we select those k elements. All right. What have I done? Ooh, child, things are gonna get easier. And I forgot to, as per usual, I forgot to mod it. 10 times 9, what? 10 to the 9 plus 7. Ooh, child, things are gonna get easier. All right. Speed it up. Slow it down. I've never said it was, well, I really don't actually know. But what is the run and space complexity of this problem? Yikes. Actually, I don't know what the complexity is here. For space, it's nothing. Space is constant, okay? For time, though, like, what is the compute time of... This is a constant operation. Power operation? So it's weird, right? Because, like... You guys tell me in the comments, what is it? Is it constant? Because sometimes, like... To do these operations and multiplying isn't constant. It's dependent on the actual elements, right? So the actual runtime is dependent on what's given, right? Because you actually, like, the computer has to do the calculation, and that's going to take time, and it's dependent on what's given. So it's definitely better than n. So I'm going to say big O of n, because it's better than n. Well, n's given this way, so I actually don't know. I apologize, guys. I don't know. Let's see what someone smarter than us is saying. See if that makes sense. This guy is... Okay, he did the exact same thing. Ooh, child. So he doesn't even care to give you the details. I don't know what's going on. All right, guys, that's it for today. No one ever makes it to the end of the video anyways. If you made it to the end of the video, please drop in a comment and say, I made it to the end, because who would do that? Later, play.